We're live now.
There we go.
I think we're live now. Sorry about that, everyone. Technical difficulties. We had started the show earlier, but Marley realized we're not actually talking to anybody. So let's start this over again. Hello, everyone. Welcome to Ask an Astronomer. And my name is Matthew Cimone. I'm the head interpreter here at the HR MacMillan Space Centre and Planetarium. I'm joined, of course, by our astronomer, Marley Leacock. I'm very excited about this episode. I'm filling in for Michael Unger, our program coordinator, who's away doing a science fair with youth. I think in Alberta somewhere.
No, they're in Ottawa right now.
They're
They're
in
in
Ottawa
Canada.
right now. Okay,
They're
they're in
doing
Ottawa.
Canada-wide science fair in Ottawa, and
Canada-wide
he
science
he
fair
was
in
the
Ottawa.
chaperone
Awesome.
for some BC kids, I believe. So
Nice,
he's
nice.
out there doing science with them.
Doing science with them, but that means we get to talk about the science of science fiction. And I was glad that I got to come in now because that's one of my favorite things to talk about. And we're going to talk about one of my favorite movies. I know it's also one of your favorite movies, which is the science, or lack thereof in this case, of Armageddon.
My favorite movie. Any movie with the Wikipedia subtitle of scientific accuracy gets a good vote for me, of which this movie does have, and it's very long and it is not very accurate, but it is a great movie nonetheless. So for our ultimate episode for the science behind science fiction, as we close out the month, as that's been our theme the past few weeks, I decided to hold everyone here hostage and make them all listen to me ramble about Armageddon and why it's a great movie and why the science behind it is very, very fun. So to start us off with, just the premise for anyone who hasn't had the joy of watching this movie yet, the idea behind the film is that there is an asteroid on a collision course with Earth. And it's large enough that it will wipe out all life on the planet. They refer to it as a global killer in the
Global
film.
killer.
Yeah. Their solution to this is, of course, nuclear bombs. This came out in 1998, so big explosions were big, as was destruction at the turn of the millennium. And their way of success is, depends on how much you follow the film and how much you follow the science, and I guess what your definition of success is by the end.
That's why we put Bruce Willis on the job. That's why.
Yes,
that's who this is going to get done.
They'll get to. He's there, and it has one of the best soundtracks ever. Shout out Aerosmith.
Oh, yeah.
It also has one of the best lines ever in any movie, which is, "Oh man, what are you doing with a gun in space?" Which is very funny, considering that in this scene there's a nuclear warhead about to go off. But the gun's the problem. Very good. So in Armageddon, the asteroid is described as the size of Texas, and it is 18 days away from being on a collision course with Earth. So right away, the first thing that sticks out to me is the 18 days away. For an asteroid of that size, the size of Texas, which we'll get into in a second, typically we would spot that pretty quickly. That would be pretty big, especially if it were only 18 days away. For this to have happened, the film explains it as a rogue asteroid, where it was further out and it was hit by a comet or some such object and knocked into a new orbital path, which put it on a collision course with Earth. That's a good enough explanation for me. That is something that could happen. What is more of a problem is this idea of it being the size of Texas, because what does that mean? In astronomy, when we talk about size, we usually talk about mass or density, not Texas. So what is that?
How many giraffes wide is that, Marley?
Yeah, exactly. Texas across is about 1,245 kilometers, and lengthwise it's about 1,290. So it's pretty big. We have to determine what that means, though. What size of Texas are we thinking about? It has a surface area, though, of 676,587 kilometers. So already there's a couple of sizes of Texases we could be working with in terms of this asteroid. The first scenario is that it's an asteroid with a diameter the largest size of Texas, which I took to be the length of about 1,290 kilometers in diameter. This is very big. We could also be looking at, instead, the asteroid as it's coming towards Earth. This view, our viewing angle, would give us what we call the cross-sectional area. So we'd be looking at the face of a larger sphere. That cross-sectional area, if it's the size of Texas, could have the surface area of Texas. All of Texas could fit inside of that. That would be the same surface area, which is 676,587 kilometers squared. Doing the math, geometry, don't worry about it. That works out to an asteroid with a diameter of 930 kilometers. So
Okay.
still quite large, not as big as, 1290. The third option is that we are looking at a sphere whose area is the same as the surface area of Texas. So think of Texas, the surface area wrapped out onto a sphere. That area, if you go through the math, will give you a sphere with a diameter of 460 kilometers. So still quite big. So these are our candidates for possible asteroid Armageddon possibilities. Yeah.
For reference, Marley, because probably one of the asteroids that we're most familiar with in terms of impact on the Earth and causing Armageddon level damage is the one that killed the dinosaurs. It's about 65 million years ago. So, for perspective, how big would that asteroid have been?
They estimate that one was anywhere between 10 to 15 kilometers.
So that's a
So,
pebble. That's a
so that's
pebble by
it's
comparison to
it's
this.
a piece of this that has fallen off, is that one,
Right.
right? And
Okay.
that
Okay.
one, that one was enough to do significant damage to the ecosystems. Earth itself was okay, but the ecosystems is what happened
So,
to be
in any
destroyed.
one of these scenarios, we're done.
Yeah, global
Okay.
killer is an accurate term
All right.
in the film.
All right.
But how, looking at these sizes, like these are very big, how do these compare to the actual asteroids that we have in our environment? So this is a list of asteroids people are familiar with. I know eagle-eyed viewers will see that Ceres is on this list. Ceres has since been reclassified as a dwarf planet, but at the time of the film, it was still an asteroid. So I decided to put it in there also just to give us a sense of scale. So Ceres has a diameter of 946 kilometers. For Vesta, which is now currently the largest asteroid that we know of, has a diameter of 525. 16 Psyche, which is a very metal-rich asteroid that the Psyche mission is set to explore, has a diameter of 220 kilometers. Asteroid Bennu, which was the asteroid that OSIRIS-REx visited and brought back samples from, which they were able to open the container up very recently and actually get the material. That has a diameter of 0.525 kilometers or 525 meters. And asteroid Apophis, which was at one point the highest risk for impact with Earth, has a diameter of 335 meters. So it's quite small. It has since been moved off of the potential hazardous asteroid list. It's no longer of risk to Earth. We're actually not going to collide with it at all. This happens very often, things being moved on and off of lists. So to compare our asteroids, 460-kilometer diameter would put it in third place between Ceres Vesta. 930 would fit between Ceres and Vesta, and 1,290 kilometers would make it the largest asteroid ever, right? Like that is too big. Things in the asteroid belt don't get that big, which is why their explanation of this came from further out makes sense. It stops making sense when you think about what it's made out of, because it's made up of mostly iron or iron ferrite, as they call it, which we will get into when it comes to what are we going to do about the thing. So
Right. So
that's
if we didn't see this by now, it's because someone was sleeping on the job. Like we probably should have seen an object this big traveling through the solar system already.
we probably should have. Yeah.
Right.
Like
Okay.
this is very, very big. In the film, they say that the sky viewing budget is only enough to let them view 3% of the sky. That's like way lower than what NASA is actually able to see. NASA has eyes on a good chunk of the sky. So they make it much more dire than it is. So their plan is summarized very nicely by Billy Bob Thornton here, which is you drill, you drop the nuke, and you leave, right? So the plan in the film is to blow this up. The crew is meant to land on the asteroid. So Bruce Willis and friends land on the asteroid. They drill to the center, which is not actually the center. In the film, they get to 800 feet down, I think is the mark they want to hit,
So not even close.
which something
Yeah.
that is like, yeah, not even close. It wouldn't, yeah. But let's assume for the sake of this, that they drill to the center, they drop the nuclear warhead, they detonate this high yield nuclear weapon, which will then split the asteroid in half, saving the Earth.
Cool.
Yay, right? That's the plan. So what do we know? We know that the asteroid is 1,000. Let's drop the 290. Let's just do orders of magnitude to make it easy. What about 1,000 kilometers in diameter? We know that it's moving at a speed of 10 kilometers per second. They tell us in the film that it's made up of iron ferrite, which we will take to just be iron materials. and that what we want it to do is split into two equal hemispheres after we blow it up. We want it to split into two equal hemispheres that will clear the Earth. And that clearance distance they give is 640 kilometers. They give it in miles because it's an American film, but kilometers is SI. So we're sticking with metric. The bomb is detonated at what they have a go, no-go zone, right? So just like how when we launch rockets, there is like a go, no-go period. There's a go, no-go zone where once you cross this distance, no matter what they do, that asteroid's going to hit Earth. And that distance is 101,000 kilometers. So that's where the asteroid gets detonated at. That's its distance from Earth. Which, yeah, it does happen. It's right on the edge. It's a very tense moment in the movie.
Of course, yeah.
So the question is, how much energy is needed to take this 1,000 kilometer diameter asteroid and split it into two equal hemispheres that will pass harmlessly by the Earth? So I actually am not the only astrophysicist who has thought about this and wondered about this film. There was a group of master's students from 2011 who actually wrote a paper, a little letter about it. Ben Hall, Gregory Brown, Ashley Back, and Stuart Turner from the Department of Physics and Astronomy in the University of Leicestershire. I'm probably pronouncing that wrong because it's English and it's got all the E's and the I's. They wanted to determine how much energy and how strong of a nuclear warhead would be necessary to accomplish this task. And so the math that follows is taken from their paper. And there's a couple of things that you need to keep in mind while we go through it. Number one, we are ignoring a lot of stuff. So if you ever taken physics class in high school, they go like disregard, air resistance. We're doing something like that. We are ignoring the binding energy, which is what holds the asteroid together, and the gravitational effects from the Earth, right? Because Earth would pull these two chunks towards it, and it would also begin pulling on the asteroid, causing it to accelerate in speed. So keep that in mind. So basically, nothing is holding the asteroid together, and nothing will try to pull it back together when it splits up.
So probably this is a conservative estimate of how much energy is actually needed.
Energy.
Okay, all right.
Yeah, very conservative estimate of what's needed. Imagine we're thinking of the asteroid as like a loose pile of just stuff, of iron.
Okay.
But in reality, there's a lot more going on. Also, we're imagining it to be a sphere. It's not spherical. In the film, it is not it's not spherical. But in physics, we imagine spherical cows. We can imagine spherical asteroids. So easy enough. They work out this equation for the energy necessary to detonate, to split this asteroid up. So this is, I'll break it down. E is the energy required. This 2/3 pi r squared is the volume of the asteroid pieces, right? So what we are working with, how much space they take up. Rho, which is that, very curved P, represents the density, which is about 7,000 kilograms per meter cubed. That's the estimate they use for iron ferrite. They don't use the number for full iron because they refer to it as iron ferrite material. So accounting for, there's probably some other stuff in there.
Okay.
This capital R is the clearance radius. So that's the distance that we want these halves to pass Earth from, which is the radius of Earth plus that 640 kilometers, because you have to account for the fact that Earth takes up physical space, right? And we want to be off of the surface, not 640 kilometers from the center, because then it's still
bad.
Yeah, that's still bad.
Okay.
This V1 is the pre-detonation velocity, so how fast it's going before it detonates, which is 10 kilometers per second. And the capital D is the distance from Earth at detonation, which is 101,000 kilometers, right? So a lot of these values are given from the film, the speed, the clearance radius, and the distance from Earth. The density has been taken from just known values that we know of. This works out, the energy necessary to split this thing up works out to 8 times 10 to the 26 joules of energy. So that's 8 with 26 zeros after it.
It seems like a lot.
It's quite a lot. In comparison, Big Ivan or Tsar Bomba, which is the largest nuclear warhead that has been detonated on Earth, released 2 times 10 to the 17 joules of energy.
Okay.
In actuality.
We're missing a lot of zeros still.
We're missing a lot of zeros, yeah.
Right.
in theory, it could have gotten up to twice that amount. So 4 times 10 to the 17 joules of energy. All nuclear testing as of 1996, so 2 years before the film came out, was 2 times 10 to the 18 of joules of energy, which is still like we're missing quite a lot, nearly 10 orders of magnitude still missing from this. The energy released by the sun in 1 second of sunlight, 1 second of luminosity, because we measure energy from the sun in watts, which is joules per second. So just 1 second is 4 times 10 to the 26.
Okay, so more than a second worth of whole sun energy output.
About, yeah, twice the amount. Yeah,
Right.
about 2 times. The 2 seconds worth of sun energy would be necessary to split that asteroid into 2 for it to pass by harmlessly by Earth.
So
and
that's
that's
like
a conservative estimate, given that what we're ignoring.
That's probably more energy output than from like our entire civilization throughout its entire history, I would imagine. There was like I saw a similar video that was done in some calculations. I can't remember who did them now, but they're looking at like when Alderaan gets blown up in Star Wars by the Death Star, and same thing, like how much energy you actually need to take something and split it apart in space. And it was like 3 full minutes of the sun's output worth of energy to blow something apart.
Yeah.
So
And
like
Alderaan's
that's a lot of
complicated
power.
too, because it's a full planet, right? So you
Yes.
have like crust, mantle, core, right? That all have different properties, all have different densities, are all different materials. So it's a lot more going on than just like a metal rock, a metal asteroid just hanging
Flying
out in
through
space.
Yeah.
Like it's a tremendous amount of energy, and so probably would not have worked. The science does not work in the movie Armageddon. But it's still fun, and it lets us kind of think. It's so much fun. It lets us think a little bit more about planetary defense, because there's another film that came out in 1998, Deep Impact, which has a very similar premise. Right, there is something heading towards Earth that is going to collide with Earth that will wipe out civilization. I think, but in that movie they call it an extinction level event rather than a global killer.
Global killer. We get hit by part of that one in that film too.
Yes, in that one you get hit by part of it. So that film, there was clearly something going on in the cultural zeitgeist at the time about planetary defense.
We were really worried about rocks from space.
Really worried about rocks, really worried about outbreaks, really worried about a lot of stuff in the pre-2000s. So this idea of planetary defense is actually something that NASA thinks about and agencies around the world do think about. And it differs slightly from, differs a lot, but the premise is still there in Armageddon. It just looks very different. Planetary defense in reality requires a lot of international cooperation, right? In the film, it's America. Like, they are the ones that are fixing it,
Flags waving in the background.
Exactly.
And everything.
Freedom and independence, like it's America that does it. In reality, because it's a global threat, it will require global cooperation to figure out what we are going to do about it. It also requires a lot of time. Unfortunately, 18 days for something that massive, there's no way that we could come up with a plan to save the planet in that time, right? 18 days is too short. So it requires a lot of lead time. Deep Impact, they have 2 years, right? Which is much more reasonable time frame to figure out what you're going to do. With time comes detection and monitoring. So you have to be watching the sky, which they kind of allude to in Armageddon, but they way underestimate the amount that NASA is able to do. And then there's the way of dealing with an object coming towards Earth. And it does not involve nuclear weapons. That causes actually a lot more problems than it would give solutions, right?
Really? Blowing up nukes in space is a bad idea? No.
It might not be great. There's the problem, though, if something goes wrong with blowing something up with a nuke, now you have radioactive material heading towards Earth. So not only
icing right on top there.
Yeah, just a little extra. So the way that the current thought of dealing with it, there's a couple different ones. There's a lot that deal with, I've seen like solar sails, like attaching a solar sail to it. I think that's one of the Deep Impact solutions is one of the scientists like, oh, we'll attach a sail to it and we'll move it. Or that might be Armageddon. I get them mixed up sometimes. That is also possible. We have seen solar sail technology work. Like it does work. There's ideas around gravity, but one that we have tested is the kinetic impactor. And that was tested with DART, which is this mission that we talked about a while ago. There's a few episodes on it because it was the testing of new science. And what DART did, the double asteroid redirection test, is that we discovered an asteroid, Didymos, that had a moonlit asteroid, Dimorphos. So Dimorphos orbited around Didymos. These asteroids were close enough for us to get to, which made them a good test. They were also not on a collision course with Earth, which also made them a good test because we're not risking launching something onto a course that will then impact us. So what was done is that the spacecraft DART was launched at Dimorphos and just collided with it, just hit it, going at a specific speed in an attempt to knock it onto a new orbit, right? Using Newton's laws of motion, every action, there's an opposite equal reaction, and also that energy has to be conserved, all these different physics properties. If DART hit Dimorphos, it would push it, right? As it hit, there would also be a pushback. Dimorphos would move into a new orbit. And it was successful. The previous orbital period that happened with Dimorphos was 11 hours and 55 minutes. To be considered a success, NASA wanted a change of 10 minutes. The resulting orbital period was 11 hours and 32 minutes. So they did knock it onto a new orbit. And these are pictures taken by the spacecraft as it was heading towards the surface. So I watched this live. And it was very cool to see the images coming in. This is the second to last image in the bottom right there. The actual final image is some rocks and then just like a red line, like because the space it crashed as the image was being transmitted. So all that information was lost.
So to be clear, this isn't this is not an explosive. This is we're just ramming something into the surface as a kinetic impact.
Yeah, no explosions, just crashing into it, just pure kinematics, pure physics. Just if we hit it, it'll move, right?
Okay.
Because objects will keep on their paths unless something else, an outside force, acts upon them. And we've introduced this outside force of a spacecraft crashing into the surface. How we detected this was a success was by looking at the period of the moonlit asteroid. So there were other CubeSats on board DART that were, ejected before impact. Like a cube was one of them, and it observed what was going on. So this is the observed new orbit here. And so this is transit, right? If you've looked at exoplanets or looked at any detecting of exoplanets, you have a brightness, and as a planet passes in front of the star, the brightness will dip, and then it'll go back up to normal after the planet completes its transit. Well, the same thing happens when objects pass in front of other objects, in this case, a moonlit asteroid passing in front of its asteroid. You will see a dip, and then the brightness will go back to normal. So on September 29th, this was observed from the new 11-hour, 23 minutes orbit. Whereas if we were still looking at the old orbit, we would expect to see a dip here. And the same thing continued into October 4th. So we had reliable information that we had changed the orbit of this moonlit asteroid. What was also cool about this impact, though, which kind of is something to consider if we were to use this as a method of defense, is that this impact ended up creating a bunch of boulders off of the surface of Dimorphos. This is a Hubble Space Telescope image. I'm not sure how clear it's showing up, but these little dots are little boulders of debris that have been moved off, that were, because of the impact, if you look at the surface, it's very rocky and it was loosely held together. So when it hit, a lot of stuff came off. The total mass of the boulders at the time was about 0.1% the mass of Dimorphos. And the numbers, the sizes, the shapes of them were consistent with anything that had been knocked off the surface from the impact. They're most likely not shattered pieces of Dimorphos itself. They were probably more likely they were pieces of boulders that were on the surface that got lifted up, and it had enough escape velocity to leave from impact. This helps give an estimate for the size of the impact crater DART would have left. They're not too sure exactly how they were moved from the asteroid. It could have been from an ejecta plume. It could have been a seismic wave from the impact that moved through the asteroid that shook the rubble loose from the surface. You'll have to look a bit longer. I didn't check to see if there had been an updated paper. This is from 2022. But it is still something to consider, especially if this will be a method of planetary defense. And for reference, Dimorphos is 160 meters in diameter. So it's still not even at that 460. It's very, very small. It's a
It's
tiny
not the
little,
size of Texas.
it's not the size of Texas, no. So that's something to consider if we are going to use that as a method for planetary defense. Could we possibly end up with smaller pieces of debris that end up coming through our atmosphere? And how big could those pieces of debris be? So
Right.
nuclear weapons, unfortunately for Armageddon, that's not the answer. But kinetic impactor technology works pretty well. It does work. We tested it, and it's pretty cool.
Yeah, but maybe not the greatest for action films. I can't imagine that they're like, okay, and then they're like in a room looking at like transit data. That just, that's cool, but maybe not action movie cool. So
No, definitely
yeah,
not for action movie. Even
yeah,
Deep Impact uses nukes, so I will
yeah.
consolidate that.
Or
But
having Bruce Willis put like a solar sail on the asteroid, and then they kind of watch it, see if it's changing
watch
direction
it. Yeah.
over time. We did it. Awesome. Well, this is amazing. Thank you, Marley. This is really cool. I do love that film, and I think having spoken, we've interviewed several people, myself and another project, who are working on. They're science fiction writers or scientists that inform science fiction, and they say that at one point sometimes the sacrifice has to be made for the story. They don't always go together, but it makes something really cool for us to watch. But I think it's also neat on this end to go back and actually go through it and figure out, okay, like what would actually be needed for what we're seeing on there to work. I imagine that's what happens with the group that put that paper together. Probably sitting around at dinner one day and being like, how would Armageddon work? How do we blow up this asteroid? And then it ends up
Yeah.
in textbook questions or whatever later on for students too.
It's great. It's great. I think like in the film itself overall, I found another website because I was looking all over for information because I was like, I cannot be the only person. Like there's no way. It was just me who was like, what's going on here? There was one gentleman, his website is named Dino Jim. He's a geologist and
I know
and
Jim.
and paleontologist. And he has a whole page of like different mistakes or different points of science in Armageddon. And the first thing happens 37 seconds in. He's like, this map is wrong. So it's fun. I think no matter what kind of scientist you are, it's fun to watch. It's still an enjoyable movie, but now you know how we might potentially actually deal with a threat like that.
Right. One point I was going to mention. So you talked about how drilling down inside of the rock probably wouldn't make any difference. And if I remember correctly, and I can't remember now if this is from Deep Impact or Armageddon. Same thing. I put the two together. But they mentioned that, like, I think they use the example of putting a cherry bomb in your hand. And they're like, if the cherry bomb explodes on the outside, it doesn't really do anything. But if you hold it in your hands, it'll do a lot of damage to your hand. So is
Yes.
there actually any kind of like multiplication of the force or the impact on the asteroid by putting the rock the down inside? Is it going to crack it open? What do we actually really need to
Oh,
put it inside at all?
yeah, because if it's just a surface detonation, you're just gonna create a giant dent in the surface. Like the
Right.
idea of it going to the center was that as it explodes, which it explodes outwards, it's moving through the rock itself, right? Whereas if it's the surface, part of it's moving through the rock, but the rest of it's just going out into space and
Yeah.
not doing anything. And so in the film, they say they need to drill to 800 feet, I think, which is less than a kilometer. And this thing is, if we're doing the largest possible asteroid for dramatic effect for you,
Yeah.
Bruce Willis, it's like nothing. Like it wouldn't do anything, right?
Right.
But for the sake of the movie, it works out.
It works out. I love the fact that the drill has like that. It's like that skull gear shift handle on it. Like
Yes,
shifting gears, like it's a car. I don't know
exactly.
anything about drills. I don't. I've never seen one on a drill like that, but I don't really know. Very interesting. Them trying to get down inside. And then I think you were mentioning, you and I were chatting before, and we were talking about just like the twisty design of the asteroid, like how
Yes.
like evil and foreboding it looks. Do comets actually look like that? Like if I were on the surface of a comet, what would we actually see down there?
Oh, well, we've imaged surfaces of asteroids, and they don't look like that at all. They're usually just like piles of rubble. Some of them they look different, but like asteroid Ryugu and asteroid Bennu look very, very similar to each other. They both are slightly spherical. They both look like they have lots of little tiny boulders on the surface. They look like kind of loose rubble, gravel piles. That one is interesting because it's explicitly mentioned to be mostly metal. So one to think about would be Psyche, because that one we know and believe it to be mostly metal. We actually think it might have been the core of a planet that never was, right? So like how
Wow.
iron has or Earth has that nickel iron core, Psyche might actually be the core of a planet that never came to be. That would be one of the closer approximations. But space doesn't like jagged edges. Like physics doesn't like jagged edges. Things
Right.
tend to smooth out. So
Yeah.
it's weird that there's a lot weird with this movie if you think about it for too long. Like, why is
Yep.
there fire? There's no atmosphere on the asteroid,
Yeah.
so the fire can't happen. Yet it does. So
Drama likes jagged edges.
drama
That's
likes
why.
jagged
Yeah,
edges,
that's why
yes.
physics might
And
not like
dark
round edges.
purple for some reason.
Oh yeah, so
Yeah.
foreboding. One other question I was going to ask you, Marley, before we wrap up. So movies like this and the way that we, I think, because of them, perceive asteroids or objects in space as sort of these like menacing things that might come to get to us and wipe us out. But obviously, we're sending missions to them to learn something. So when we are sending robots like Bennu that are going out and sampling asteroid material, what is it that we're trying to learn? What can we learn from visiting these objects in the solar system?
Yeah, so asteroids, like what they are is that they are remnants from the early periods of our solar system. So it's before all the planets, formed what they are today, there was a lot of just debris left over from when the sun first began. And a lot of that debris went on to become asteroids and just piles of rock, basically. And so by studying them, we are able to learn about the very early time of our solar system. A lot of evidence that we would have on Earth has been washed away because Earth is such a geologically active world with water and an atmosphere and us, making changes to it. But asteroids, they don't have really anything going on with them. They're out there like time capsules waiting for us to learn and take samples from them. For OSIRIS-REx, we wanted to just get a sample from an asteroid, figure out what it's made of, but also try to trace it. A lot of it comes back to finding out how life started, trying to figure out where we got these ingredients. Bennu is very high in carbon. It's a high carbon asteroid. And so there's quite a lot of material there that's carbon, but they also found a lot of traces of water as well. And so this mystery of trying to figure out how Earth got its water and where it came from and what the early solar system was doing is why we go out and study these asteroids.
I think of that, it's almost very opposite to the way we think about asteroids and comets, and because we think of them as like ending our story, like wiping us out. But if anything, they're actually helping us to better understand what our story is, like how we got started, how life maybe began on Earth. And does it also suggest then, if we're looking at these asteroids and they are typical of solar system asteroids, does that give us a sense of how common those materials might be in other solar systems as well? Is that a safe assumption to make?
Well, we can only base off other solar systems based on our own, right? So similar to how we like understand stars and understand planets and life on other planets is all based on what we know. So the more we can figure out about our own solar system, the better we can understand others, even if they end up being completely different, right? That still opens up an avenue for us to understand. And like, yeah, we tend to think of comets and asteroids as like the endings, but I think everything in space, like you're very familiar with this, with the shows that we do, is that anything that ends also begins something else, right?
Sure.
Like when a massive star dies, yes, the star dies, but the explosion from that can trigger star formation somewhere else, right? So it's all connected, right? These things may be the ending of our world if one the size of Texas, hits us, but it may have seen the beginning of our world too, right? So it's
Okay.
all things to think about. Very poetic. Somehow
Yeah.
Armageddon became at the end of this show.
Q Aerosmith.
Yeah.
But then I guess that's true, because if a rock hadn't wiped out the dinosaurs, which were
Mammals
arguably like,
wouldn't have been able
we
to
wouldn't
do what they
we
did.
wouldn't be here. Yeah, we wouldn't be here. So thanks, asteroid,
Yeah.
for hitting the reset button on our planet so that we could be here later on. Well, this has been great. Thank you so much. I'm glad I got to sneak in here at the end of the Science of Science Fiction episodes. This is the last of the Science of Science Fiction
Yes, it
series,
is.
right?
Yes, it is.
Do we know what we're doing
I
next week?
can't remember it's not next week. It's 2 weeks from now.
2
This
weeks
is
from now,
Michael's
sorry.
part, so I never write this down, but it's 2 weeks from now.
Cool.
I don't know what we're doing yet, but stay tuned. It'll be fun.
It'll be fun. So check out our social media. 2 weeks from now, Thursday, Ask an Astronomer, starting at 4 p.m. Pacific time. And of course, if you're in the neighborhood of us here at the planetarium, you can always come and visit us in person. We have our daytime programming during the day, and then on Wednesdays and Friday nights, we have a telescope. So you can actually come and visit us and see our telescope and see stars and planets and galaxies for real. So come out and see us. Thanks so much for joining us, everybody. Thank you to Marley Leacock, our astronomer, and we'll see everybody either in person or in 2 weeks from now for Ask
And
an
thanks to
Astronomer.
Matthew for jumping in and hosting.
Oh, I always love talking about my favorite things with people. So any